Alright, with the Euler-Lagrange equation done, I need to deal with a very important point, which is every time you teach this course you get people who mispronounce Euler's name and they pronounce it Euler. And so I very strongly encourage you not to do the teacher in Ferris Bueller's Day Off, Euler, or I'm just going to laugh at you. It's Euler. We can have endless debates about which way it should be pronounced, but that's the convention and that's the way we're going to do it. Okay, so make sure you're doing it properly. If you haven't seen Ferris Bueller's Day Off, then maybe it's time for you to get a movie night. Alrighty. Okay, so we have our Euler-Lagrange equation now, really powerful tool. In the next half hour or so, we're going to go through and use it for a couple of examples. But first, what I want to do is just generalize it one step further, because if you have a look at the equation that I've got on my notes, I've got it written in terms of x, and often when you look it up in books, you don't see it written in terms of x, you see it written in terms of something different. And what we want here is a tool that's kind of not just useful for one coordinate system, but that's kind of useful for every coordinate system you can imagine. So x, y, z, r, theta, phi, all different ways to do it. And what we do here is we call these generalized coordinates, okay? We'll really dip into generalized coordinates properly in some of the later lectures and define them really well. I'm just going to point them out quickly now so that, you know, some students like to read ahead and have a look in books, just so that you've got a bit of a foreshadowing of the way this works. So what you'll sometimes see is two different ways of writing your generalized coordinates, right? One is to generalize into a set of momenta, P of I, and a set of corresponding coordinates, Q of I, P's and Q's. We won't do that very much early in this course. Maybe later on I'll switch over to that notation just for a little bit of fun. But you'll see quite a few books where they talk about P's and Q's. The other thing that we know is that momentum is mass times the time derivative of position, right? It's mass times velocity. So instead of dealing with P, what we can do really is just hide the mass and deal with Q dot. So what we do is deal with Q dots and Q's. And we just label them by the letter I. And so then we have an Euler-Lagrange equation in here that looks a little bit like this. D over dt, dl on dqi dot minus dl on dqi equals 0. Okay. Some of you will be thinking, oh my god, it's another equation I have to remember. It's all too much to stuff in my head. Later on, I'll give you some really good mnemonics for how to remember this thing. It's actually not as hard to remember as it looks, but it's a little early to do that, so because the mnemonic won't make sense, so we'll come back to that a little bit later on. Okay, so like most things in physics, there's a little bit of a procedure to how you solve problems, and there's a procedure for how you solve problems in Lagrangian mechanics. The first two steps we're not going to deal with today. I'll come back to those in lecture 8 and define what these things are, but it would be determine the number of degrees of freedom and determine the constraints of the system. For what we're going to do today, let's just have that suffice as we need to know what the problem looks like, and for example, what coordinate system we want to use, how many coordinates we need to keep track of, is there anything that makes the motion behave in certain ways. What we then do is we select a set of independent generalized coordinates that's consistent with that problem setup. So it might be x, y, and z. We can change x without affecting y. We can change y without affecting x. They're independent variables. Okay, so we need to set that up. Then what we do is we work out what the form of the Lagrangian is. So we get this L equals t minus v. And then all we do is we write down what we call Lagrange's equations of motion, and there can be many of them, basically by plugging the Lagrangian L and whichever generalized variable we're interested in into the problem. So when we do projectile motion, in a couple of slides from now, you have an object that can go from here to here, and it might have two coordinates that you're interested in, x and y, right? Because it's moving in a plane. So you've got like an x direction and a y direction. And so what you would have is one Lagrange equation that's d on dt, dl on dx dot minus dl on dx equals 0. And you would have one connected to y. So you've got two separate equations, d on dt, dl on dy dot minus dl on dy equals 0, okay? And so you take those two equations, you solve what comes out of them, and you use that to predict the dynamics, okay? What we have here is a really powerful technique, and when we get to some harder problems, you'll possibly remember having done them in first year, things like Atwood's machine. Like if I think back to my first year courses and doing Atwood's machine, it just gives me nightmares of all the pain that we used to go through with normal forces and all sorts of things to try and tease out this problem. Lagrangian mechanics really shows its power there because it just makes all the pain go away. We're going to do a couple of examples today, and it's a little bit like trying to light a barbecue with napalm. It's massive overkill, but we're kind of going to do it just to illustrate the point, okay? So the first one I'm going to do is actually what I consider to be a derivation, or part of the derivation in a sense. What we've done so far in the first half of the lecture was basically make a statement that, you know, nature chooses a path based on the fact that it minimizes the action. And then we showed that it popped out this Lagrange equation. But we haven't shown that that actually gives us anything that connects back to what we already know about mechanics, right? And so we've still got one thing to prove, which is that this new architecture that we built of Lagrangian mechanics ultimately reduces to Newtonian mechanics in the end, okay? And you can imagine this in the same way as when you talk about special relativity equations, when you make the velocity go from being close to the speed of light back to, you know, something that's a lot smaller, should reduce back to Newtonian mechanics. And you have the same thing with quantum mechanics, right? If you take quantum mechanics and an electron, and you make that electron's mass go to the size of, you know, the mass of Jupiter, then quantum mechanics has to switch off and it has to go back to things that we know, okay? So these limits are always really important, and the same thing holds here. Lagrangian mechanics should give us something that connects to Newtonian mechanics in a proper way. Okay, so what we're going to do is the simplest possible problem you can imagine for Lagrangian mechanics, and what I'm going to show is that it just pops out Newton's second law, okay? Halfway consistency check, halfway an example of how to use the technique. So what we've got is a free particle of mass m in some 3D potential. We don't care what it is at the moment, except that now we have to worry about coordinates x, y, and z, okay? So we'll do this as a three-dimensional problem rather than a one-dimensional problem, just to show you what happens when we deal with that. Okay. So step one would be to work out what our degrees of freedom are. And in this really simple case, there's actually 3 degrees of freedom, right? There's z, x, and y, or z, y, x, whichever way you want to call it, doesn't really matter in the end. Fun with video cameras. Constraints, there are none, so we don't have to worry about that now. Particle can go wherever it wants, subject to the potential. And then the coordinate system that we're going to use here makes perfect sense, is Cartesian coordinate system, x, y, and z, okay? Obvious choice unless you've got a better choice to choose. So, probably put it as step one, specify the problem, right? Specify problem in the coordinates. And in this particular case, what we would have now is Q1 is just x, Q2 is just y, and Q3 is just z. And you don't necessarily need to write that down if you're doing an exam question. It's usually pretty obvious when you set your notation up what you're going to do. I'm just highlighting it here so that we can just walk through these steps one by one, because what you want to do in dealing with these problems is actually have a sequence of steps that you follow. Okay. So the second part is we need the Lagrangian. And that means we need to know what the kinetic energy is. And the kinetic energy here is pretty simple. It's a half mv squared, and of course v has components in x, y, and z. So it's just going to be x dot squared plus y dot squared plus z dot squared. And then our v is just a v of x and y and z, completely unspecified. We don't care about it for the moment, so let's deal with that. And so our Lagrangian is basically t minus v, so it will be a half m x dot squared plus y dot squared plus z dot squared minus v of x and y and z. Okay. Now we've got that Lagrangian, all we got to do is write down Lagrange's equations. There's going to be 3 of them. There's one in x, there's one in y, there's one in z, and you can see from the symmetry of the problem so far that the one that we get in y and the one that we get in z is going to do exactly the same thing as the one we have in x, right? So we can just deal with the one in x and then carry the answer across. So we'll just deal with x. So the first step is basically to get your derivatives of the Lagrangian. So we need dl on dq, and it will be dl on dx in this case, which is just minus dv on dx, right? Because the only thing in that Lagrangian that depends on x is the potential, and we need to take derivative with respect to x for it. And of course, you know from earlier lectures that dv minus dv on dx is just a force. Okay, so it is just the force in the x direction. The other one we need to get here is dl on dq dot, and it will be dl on dx dot in the end. And if we look up at our Lagrangian, that term comes out of the kinetic energy. It will be the y and the z terms disappear, the 2 comes down from the square, and we've got mx dot. Okay? And so then what we do is we compile this into our Lagrange equations. So it's going to be d on... let me just clean this up so it matches my notes. Because it's 2 terms equal to 0, you can change the sign, you can move them around, and so you'll see slightly different rearrangements of this, just relying on the fact that there's the 0. So d on dt, dl on dqi dot minus dl on dq dot dqi is equal to 0. It's our Lagrange equation. In this particular case, these things in the bottom here would actually be x's. So let's just change that so we don't have to rewrite anything. Actually, that should not be x dot, that should just be x. Okay, and then we put this in, right? So what we've got here is d on dt of our term for x dot, which is mx dot, minus f of x is equal to 0. And of course, we need to take this derivative over on the left. The mass is independent of time, so this becomes mx double dot minus f of x is equal to 0. You can pull one of the terms to the other side, so f of x is equal to mx double dot, which, as you know, that's the acceleration. So what we really have here is just mass is equal to, the force along the x direction is mass times the acceleration along the x direction. We've got Newton's equations out, okay? If we do this for y, if we do this for z, we get the same thing. F of y is y double dot, f of z is mz double dot. Fairly simple. We've basically just shown that Lagrange's equations will pop you out for just a body floating in space, the Newton's laws. Okay? All right. So with that done, let's do a second example. Rocket Man, burning out his fuse up here and down. All right, projectiles. We'll do them projectiles Lagrange style. So, classical projectile motion problem. Kim Jong-un loves them. So we have x in here, y over here. We have some object following a parabolic path, and hopefully your enemy is here somewhere. And Uncle Kim is down here near the origin of our parabola. Very classic problem that you have in first year physics. And so step one, let's work out what the problem is. We know what the motion is. It's an unconstrained motion. There's nothing holding it in place. There's nothing making it follow a particular path, like, you know, being tied to a string or running along a wire. We have two coordinates that we care about, x and y, and it doesn't matter which way we point it. We can just decide that there's a plane that's along the direction that we point our projectile, and it's going to go along that direction and it's going to go up. So we can basically just make this 2 degrees of freedom and go that way. Okay, so you can imagine in some sense there's a constraint in here which basically says that the motion can't be out of that plane. Okay, we'll talk about constraints a bit later, but I don't want to get into them this early in the game. So we've set that up. What we need to do, so step one, set up. Step two, we need to get L. And that means we need to get T and V first, right? So our T here is just a half mv squared, same as it always is. But now we only have two directions to worry about, x and y. So we can write this thing as a half m x dot squared plus y dot squared. Like so, okay? And then our potential energy is, as you learn in first year, it's mgh. Or here we're defining h as y, so we're just going to call this mgy and rely on the fact that y is equal to 0 when the motion starts. Okay, so we're just going to call this 0 down here. Okay, so that's that. Lagrangian now is going to look like L equals T minus V, which is a half m x dot squared plus y dot squared minus mgy. And then the next step in this whole problem is basically to pop out our Lagrange's equations and solve, right? And that means we need to get 4 derivatives in here, so let's get them one by one. We need dl on dx. We want dl on dx dot. We want dl on dy. And we want dl on dy dot. Like so, okay? dl on dx, there's no terms in x up in our Lagrangian at all, so it's going to be 0. dl on dx dot is going to come from the kinetic energy term, so again we're going to get mx dot in here. The 2 in the square is going to cancel out half. dl on dy, there is one term in y in there, and it's minus mgy, so we're going to get a minus mg out of this. And then our dl on dy dash, or dy dot, is going to be the same thing from the kinetic energy. We're now going to have my dot up here, okay? And so we're going to get two Lagrange's equations. First one is going to be dl on dx minus d on dt, dl on dx dot equals 0, and the second one is going to be dl on dy minus d on dt, dl on dy dot equals 0. And you'll notice I reversed the two terms from the last problem that I did it in this equation. Doesn't really matter. There's a 0 in the end. I can put a minus sign through the whole thing and it's all hunky-dory. It doesn't matter which way around you write it. And that's why this equation, that's one of the reasons why this becomes really easy to remember. Okay, so we can put our things into here. So this is 0 minus d on dt of mx dot equals 0, and this one here is minus mg minus d on dt of my dot is equal to 0. And this one over here, the derivative will give us x double dot. The minus sign will disappear into the 0. So what we've got is mx double dot is equal to 0. And this one on the right here, what we'll get is minus mg minus my double dot is equal to 0, which is basically my double dot equals minus mg, or just y double dot is equal to minus g. Okay? And this one here, we could actually just call this x double dot is equal to 0 too. Just get rid of the mass entirely. It's just there as a number. Okay, so let's call this equation 1. Let's call this equation 2. That's step 3 done. Now step 4, and this is what step 4 is basically the one thing that makes physicists in the end, is you do the maths and then you try to extract some meaning from it. Okay, so the last step in this is get some meaning. What is going on in here? Okay, so let's consider equation 1 first. What we have is x double dot is equal to 0. Basically it says the acceleration is 0. We can integrate that, and so if we integrate that on both sides, we get x dot is equal to constant. And what that means is that the velocity along the x direction is constant, and as you know from first year projectile motion problems, the velocity along that x direction is always constant. Okay, and if you wanted to, you could integrate that again to get you position, right? You would have x is constant times t plus a constant, and that allows you to get position as a function of time. Our second equation in here, y double dot is equal to minus g, no dot on the g. We can integrate that too, right? So it would become y dot is equal to minus gt plus a constant, and let's just call this constant 1 for the moment. Okay. What you'll realise that this is your vertical velocity, and it is equal to a constant c1 minus gt. Okay, and you'll remember your equations from first year: v equals u plus at. That's what's going on here. Okay, so this is v equals at plus u. So this c1 in here is actually just our initial vertical velocity, and often that would just be 0 in this problem, so we would just be dealing with y dot equals minus gt, right? So as we go up, we lose speed; as we come down, we gain speed, and then we nuke what's on the other end. We could integrate this again, and then what we would get in here is y is equal to minus a half gt squared plus c1t, assuming we haven't just made it go to 0, plus another constant c2, and then this constant here c2 is basically just the initial position for the system, right? If you make t equals 0, the other two terms go away, and so what we're really doing is just setting y at t equals 0. So this is initial height. And I'll let you check this for yourself. That basically corresponds to one of the other equations that you try to memorize in first year for doing dynamical systems, right? S equals blah, 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 blah. I can't remember it now. I've given up remembering them because I've got powerful tools to deal with problems that mean that I no longer have to remember things anymore, okay? But as you'll notice, out pops Newtonian mechanics. We kind of, like, what we just did here was a little bit of overkill. We basically just killed a cockroach with a nuclear bomb. But it's an illustration of the technique, and later on we'll get to places where solving the problem with the kinds of approaches that you use in first year is a lot of pain, and then using this is much, much nicer. Okay? Alright, so with the examples done, there's one last thing I want to do before I finish for today, and that is to address something that we call cyclic coordinates. Okay? And basically it comes from taking an assumption that one of the terms in the Euler-Lagrange equation is equal to 0. So let's start with our Euler-Lagrange equation. D on dt, dl on dqi dot, minus dl on dqi is equal to 0, right? We're going to assume here that L has no explicit time dependence on Qi. And what that means has no explicit dependence on Qi. I might have slipped the word time in there by mistake. Has no explicit dependence on Qi. So what that means is that our dl on dqi is going to be equal to 0, straight up, okay? All right. If this is true, Qi is something that we call cyclic, right? One thing that I always find really interesting with physics is that we have all these names for things, and then later on we never really use them very much. We'll come up later in the course and we'll talk about holonomic and stuff like that. And then that may be the last time you hear the word holonomic until, you know, for some of you one day you have to teach mechanics to the next generation. We define these things and we have to give them names, and we may not always use them all the time, but they have to exist, otherwise we don't have things in our subject, okay? So this is what we refer to as cyclic. So if this is the case, that means this term up the top here is 0, and so what we're left with is d on dt of dl on dqi dot is equal to 0, okay? And that's really easily solved. What it is basically dl on dqi dot is equal to a constant, right? So all I've really done there is just integrate both sides, same as you normally would with respect to time, okay? At the moment this doesn't have a lot of meaning, but if we look back at our original example a few slides back of a free body problem, we'll see this, okay? So let's just have a free particle. And this time what we're going to do is actually set our potential to be 0. So you can imagine just an empty universe with my little rubber basketball just sitting there floating in it, okay? Now our kinetic energy term is still going to be the same as it was before, a half m x dot squared plus y dot squared plus z dot squared. That's going to make our L, which is t minus v, just become t. So I'm not going to write all the terms again, it's the same thing. And what we're saying here is now that x and y and z are cyclic because the Lagrangian has no explicit dependence on x and y and z, okay? If we do this, let's look at dl on dx dot, right? dl on dx dot corresponds to this guy up here. It's now going to be d on dx dot of our kinetic energy term that we had up above, which is going to be mx dot, so the square on the x dot is going to pop down and knock out half. And this thing, of course, is just a momentum. And it's the momentum along the x direction, right? And if we solve all three equations in here, because there would be three Lagrange's equations, I've only just done the one in x, what we would get is mx dot equals a constant, and of course it's px. My dot is equal to a constant too, and it's just py. And mz dot is equal to a constant, and it is pz. And those three constants don't necessarily need to be the same, right? All they have to be is constant. And so what that means is, essentially, if I have my object sitting stationary in space, well, all those constants are 0. If it's moving along at some velocity, it's all of those momentum components may be different, but they're all constant, right? What we're doing here is basically saying if Qi is cyclic, then Pi is conserved, right? So here Qi our x is cyclic, so Px is conserved. Our y is cyclic, so our Py is conserved. Our z is cyclic, so our Pz is conserved. And really all we've got here is just conservation of momentum. Now if we think for a second what's really physically going on around this thing for the term cyclic, what we're really saying is that there's no force along that component, right? If Lagrangian has no explicit term in the coordinate, what that means is that there is no force acting in that particular coordinate, and the momentum is conserved. And of course the momentum is conserved when something's not subject to a force because of Newton's first law, okay? And so what we can do here is we can define something that we call our generalized momentum. And we can define it as Pi is equal to dl on dqi, okay? And this is basically just taking the observation above that dl on dqi dot, sorry, it's qi dot, dl on dqi dot is corresponding to a momentum in a problem, okay? So this is the thing we call a generalized momentum. And we get our momentum conservation laws back. We can correspondingly think our way through the maths in here. We've now got our generalized momentum. It looks a little bit like this, and that's the term in here. It's d on dt of our generalized momentum minus dl on dqi, right? Now, if we think about what dl on dqi is, we can basically pull this term over to the other side, right? So dl on dqi is equal to d on dt of this. And of course, this is generalized momentum. It's d on dt of p of I. This thing is a force, right? dl on dq dot is a force. And you know, in the explanation I just gave, we just talked about force being 0 as to y coordinates as cyclic, right? So it is a force. It makes perfect sense. It's a consistent thing. And so we can define this thing as a generalized force, right? And so if you think about now what your Lagrange equation really is, what it is f equals dp on dt. In other words, it's f equals ma. It's just second law of Newton's second law, okay? So really, we went to all this effort to work out what the, Lagrangian principle of least action, Lagrangian paths, these sorts of things. And what we end up in the end is an equation that basically just tells us Newton's second law, okay? So we've come to it via a mathematically slightly more complicated route, but it also gives us a very powerful mathematical toolkit to deal with problems, a much better one than if you don't have it, okay? All right, I'm going to stop with Lagrangians here for a moment. The next 3 lectures will be on harmonic motion systems, and some of the reasoning behind that is I want this stuff on Lagrangian mechanics to just settle in your heads for a little while, so that when we come back and hit it really hard, a lot of these concepts that we've dealt with today make a lot of sense. So in the next lecture we're going to get a bit hardcore on simple harmonic motion. It's going to be a little bit of a revision of first year, but with a bit more of a mathematical spin on it. And we're going to use that to set ourselves up for doing damped oscillators and forced oscillators. So I kind of need it as a tool for later lectures. And some of these problems we'll actually do with the Lagrangian approach just to reinforce the point, okay? So I think I'll finish there. As your Uncle Nat would say, physics in style champions. See you next time.